all managed to grab I hope you all managed to grab yourself a coffee during the break. Thank you for coming back and joining us for this final talk of this first session of today's meeting. And it's my great pleasure to welcome Elisa Visher, who's joining us from the University of California, Berkeley. So great kudos to her for joining us at what is, I think, 4:30 a.m. their time at the moment. So thank you very much for joining us today. And Elisa is going to be talking to us about the 3 T's of virulence, evolution during zoonotic emergence. And with that, I will pass over to you.
Great. Well, I'm really excited to see everyone today, and thanks for the invitation. So my talk today is going to be following up kind of on Ben and Katrina's talks, where they talked about what predicts virulence at the spillover, and then also how we see SARS-CoV-2 actually evolve. And this review paper really came out of conversations where people in popular media and also the scientific community were trying to predict how we actually would expect SARS-CoV-2 to evolve. So would we expect to see it evolve higher virulence, lower virulence, and for any of these individual fitness improving mutations, kind of what these correlated phenotype effects would be. And so me and some of my lab mates got together and we put together this review specifically looking at virulence evolution during zoonotic emergence and how theory might change in these scenarios. So first I want to introduce what we mean by virulence when we talk about disease evolution. So in disease ecology, virulence is defined as the additional mortality rate due to infection in math models. So this additional mortality rate can be affected by many factors. So during this pandemic, we've talked a lot about host factors like host age and immune status and how that can affect infection fatality rates. But for virulence evolution, what we're really interested in are these pathogen factors that control disease severity, since those are what the pathogen can actually select on and evolve. And so these might include traits like the replication rate of the virus or other pathogen within the host, the replication site, so which tissues it's primarily using, and also whether it has any immune manipulation traits. So straight off the bat, I want to introduce us to this question. So can we even predict pathogen evolution? And what do we actually mean when we say predicting pathogen evolution? Well, the most simple answer is that we absolutely cannot definitively predict how a specific pathogen will evolve, especially these newly emerged ones that we just don't know that much about the biology for yet. This doesn't mean, though, that we have absolutely no idea how pathogens in general might evolve. So this complicated reality makes scientific communication around pathogen evolution a little bit tricky because the science to be communicated really doesn't provide clear answers that can be packaged into simple explanations. And this uncertainty also seems to have created an environment where this hope for simple answers means that misinformation can pretty quickly spread. So our review and my talk today isn't trying to definitively predict how a specific pathogen will evolve, but we are going to try to go through some of these general frameworks for virulence evolution and start to understand how they depend on certain assumptions and how they can be altered by the specific characteristics of emerging zoonotic diseases and shifting selection pressures during epidemics. So first, we have seen many cases where virulence does seem to adaptively evolve. So the most canonical example in virulence evolution is myxoma virus in rabbits in Australia. So myxoma virus was released as a biocontrol agent to try to control the out-of-control population sizes of rabbits in Australia. And when it was first introduced, it had a near 90% fatality rate. Really quickly after this introduction, though, people started observing strains with lower virulence were spreading and so virulence as a whole was decreasing. And this aligned with the historic avirulence theory at the time that thought that things should always decrease in virulence because virulence was inherently bad for transmission. So by killing your host, you just weren't able to get out, so that should be always bad. However, when Fenner did more focused experiments on the system in the 50s, they actually saw that intermediate virulent strains seemed to be most competitive over minimally virulent or avirulent strains or super high virulent strains. And then also, when the rabbits started to evolve resistance to this pathogen, we actually started to see that virulence started to increase again. And so this clearly shows that there was some constraint to low virulence that disproved the avirulence hypothesis. And so Anderson and May works from the 1980s on this data to instead promote what we now consider our modern idea of virulence and transmission, and that's the virulence and transmission trade-off hypothesis. So this predicts that pathogens should evolve intermediate levels of virulence because the costs to virulence trade off with the benefits of higher transmission rates. So if we look at this graphically, we think that increases in transmission rate, so our y-axis, mean correlated increases in the rate at which infection ends through either virulence, so this additional mortality rate, or recovery. And so importantly for us here, transmission rate doesn't mean R naught, or which is the total number of secondary cases out of a single infection. Transmission rate is really kind of the instantaneous rate of transmission per contact. And so if you have a longer infectious period, this will mean more secondary infections. And so the most simple way to think of this constraint is that higher pathogen replication will cause more damage to the host because it's exploiting the host more, but at the same time, it produces larger pathogen populations. And so the likelihood of transmission is higher per contact. And another important point from this graph here is that the shape of this curve is hugely important for these models because you really need these positive saturating relationships between virulence and transmission rate to have this selection for intermediate virulence. So if things are linear, you're actually just going to see selection towards maximal virulence. And so through the virulence and transmission trade-off theory, we now think that super high virulence is bad for a pathogen because it decreases the infectious period, but super low virulence is also bad for a pathogen because this means lower transmission rates. And so how does this change in newly emerged zoonotic diseases? So we think that trade-offs still function in them, but there are a couple of things that we think will actually change during these epidemics of newly emerged zoonotic diseases. So this theory can be altered by things like kind of the fact that pathogens are coming out of zoonotic reservoirs, kind of unadapted to human hosts. And so there might be some things that predict pathogen virulence at spillover barrier, which Ben talked a little bit earlier. We also think that it might be particularly hard to predict how novel zoonotic pathogens will evolve because of this initial maladaptation. And finally, in an epidemic, the optimal strategies for virulence and transmission actually change over time and depend quite a bit on nuances of host population structure and various epidemiological characteristics. And so we organized our paper into a 3 T's framework that we think are the main 3 things to keep in mind when we try to think about pathogen evolution, specifically in the context of transmission rate and virulence phenotypes. So our 3 T's are trade-offs, transmission, and timescales. So I talked a little bit about trade-offs earlier, but trade-offs are hugely important because they explain how different intermediate virulence, transmission, and recovery rates can be optimal for a pathogen due to constraints because of links between these different traits. So in terms of transmission, we expect that transmission rate improvements are the most important selection factor for a new emerging zoonotic pathogen, but these might come with no or potentially counterintuitive impacts on virulence. And finally, the timescale of the epidemic changes the relative strength of selection versus stochasticity and also shifts the pathogen's optimal virulence and transmission rate strategies since these depend on the density of susceptible hosts. So now let's look through this together. So we have this figure that kind of summarizes our review, and we'll go into the different parts of it more specifically in the next slides. But I want to take us through this left to right just to get an overview before we start. So on this figure, we have this curve representing the number of infected individuals. So at spillover, we have very few infected individuals, and then these build as the epidemic is building, and then eventually kind of saturate out and reach this new kind of intermediate number when the pathogen moves to an endemic stage. And of course, this is very simplified epidemiological pattern. And so at spillover barrier, we think that pathogen and reservoir host traits loosely can predict virulence and transmission rates. As the epidemic is taking off, we think that this relative strength of selection is weak because of small population sizes, and also that even when there is selection, these initial mutations may be no cost. As the epidemic builds, we start to expect that the strength of selection increases relative to drift, and that transmission rate improvements should spread fastest. And finally, once the density of susceptible individuals is depleted, we expect that kind of the classic virulence and transmission trade-off theory should come into play, where selection should balance the benefits of higher transmission rates with their associated costs of higher virulence. And this often means maximizing R0, or that number of secondary infections in a susceptible population. All right, so now let's go through these different parts. So when I get into this idea that pathogen and reservoir host traits loosely predict R0 and virulence, this is a lot about what Ben Longden was talking about earlier today. And so I'm going to introduce this concept really quickly. So these figures come from a Phil Trans paper that my group did a little bit ago. And we think that, and yeah, so these dots all come from a data set of zoonotic virus associations with their reservoir hosts and their phenotypes in the human population. And so we think that certain reservoir host traits, especially the phylogenetic distance from humans, so how unrelated that other mammal is to humans, are really important for predicting how transmissible a pathogen is in human hosts, and also how virulent it is. And so pathogens from more closely related hosts like primates on the left side of these graphs are more spread more easily in human populations and also seem to be less virulent. And pathogens from more distantly related hosts like bats and rodents are less likely to spread in humans and are also generally more virulent. And so this might indicate that particularly high virulence, like the case fatality rates for hantavirus or Ebola, might limit pathogen fitness at the spillover barrier. Next, I want to talk about what I mean when I say that the relative strength of selection is weak as the epidemic takes off. So this is because the inevitably small population of infected individuals at the start of the epidemic means that stochasticity is likely to overwhelm selection to determine the spread of mutants. So we can picture this as, so if we have a pretty fit variant in one host, so it arises within that host, and it has a 90% infection rate, if that variant is super rare and it's unlucky and has been in a host that's being really good and following the rules and staying at home, then even if it is more fit, the host contact patterns where this host is only contacting one person means that it will have a smaller number of secondary cases. Meanwhile, a variant that is more lucky, even if it's not actually as naturally fit, and it gets into a host that hops onto a plane, that variant is going to have a higher number of secondary infections, even if it's actually less infectious. And so when there's very few infected individuals in a population, these founder effects and variation in transmission due to host behavior kind of stochastically determine the fate of mutants at the start of the epidemic. And so host factors are more important than pathogen ones. And then as the total number of infected individuals increase, these stochastic effects should decrease because a variant is kind of just as likely to be in any of these hosts as kind of you keep rolling the dice, so you average out this randomness. And so at that point, pathogen factors so how fit that individual variant is, become more important for determining the spread of variants. And so this can explain why we don't expect to see a ton of adaptive evolution early on in a pandemic, and also why we can see phylogenetic branching from certain places in the tree that doesn't necessarily mean that those places in the tree were adaptive versus just a host that got onto a plane and got into a new population of susceptible individuals. Next, I want to talk about why it's so difficult to predict zoonotic pathogen emergence at this in these initial phases. And so classic trade-off theory assumes that R0 should be maximized at intermediate virulence and transmission rates if these traits have positive and saturating correlations. So this is that figure from the Alazan paper that we looked at earlier. So these correlations, though, assume that the pathogen is already adapted to the host, so that all potential adaptive mutations for higher transmission rate or lower virulence should have costs in the associated phenotype. So higher transmission rate should mean higher virulence, or lower virulence should mean lower transmission rate, respectively. And these tight correlations are unlikely to actually be the case for emerging zoonotic pathogens. So kind of a good intuition building story here is the example of highly pathogenic bird flu. So we were really worried about avian influenzas because they occasionally infected humans, and when they did, they had really high case fatality rates, about 36 to 60%. At the same time, these highly pathogenic avian influenzas were really only infecting humans that had a lot of contact with birds, like chicken farmers, and not transmitting out of them very well. And so when people were really concerned about this variant, they wanted to ask whether it could evolve respiratory transmission in mammals. And so a number of groups did experimental evolution in ferrets, including these Hurst et al. And in my papers. And they found that the virus could evolve respiratory transmission in ferrets, but it massively decreased its virulence and was no longer killing them. And so this happened because the avian influenza had been using a more bird-like receptor that was located really deep in the ferret's lungs. And so when it was replicating deep in the lung, it was causing a lot of damage, but not effectively transmitting out of the host. And when it evolved to switch to using receptors that were found in the nasal terminates of mammals, it was able to actually get out of the host as the host was sneezing or just breathing. And it was also no longer causing this deep lung inflammation that was actually causing the virulence and killing hosts. So here, because this kind of new zoonotic pathogen was so maladapted to its new host, it was able to increase its fitness, both by increasing transmission rate and by decreasing virulence. And so this would have been unexpected by classic virulence transmission theory that would have predicted that these increased transmission rates must come at a cost of higher virulence. But because this virus was simply using the wrong receptor, it was able to make simple changes that allowed it to increase its fitness by switching the tissue it was replicating on, even without necessarily having costs and virulence. And so this sort of scenario where maladapted organisms can have costless initial mutations may be best explained as a Pareto front. So these Pareto fronts describe scenarios where a trade-off, so this yellow line, might ultimately constrain an organism's fitness, but phenotypes can be in this region of suboptimal phenotype space below the trade-off. So the trade-off or Pareto front separates these accessible maladapted phenotype combinations from impossible ideal phenotypes. And so this seems like a useful framework to think about newly emerging zoonotic diseases through. So in this figure, we plotted that same data from my earlier one. So these are case fatality rates and R0s for a number of zoonotic pathogens from mammalian hosts. And we adjust these metrics by virus family because we expect that each virus family will have a unique kind of intermediate virulence that it's maximized at. But when we replot our same data, we loosely see a similar trend happening where fitness does seem to be maximized at intermediate case fatality rates, but we see a lot of suboptimal phenotype space and kind of skew below a Pareto front. And so if we back up and think about what this means conceptually, so at the Pareto front, our two phenotypes trade off with each other. Below the Pareto front, though, improvements in one trait might not actually affect the other trait, as these simple adaptations can happen before costs are incurred. So emerging zoonotic diseases likely have phenotypes below this Pareto front, but we can't actually know where they sit relative to their optimal virulence strategies. So they might emerge as phenotype A or hypothetical phenotype B. And we do generally think that pathogens should improve their transmission rate, since at least initially, this is the most important selection pressure on a pathogen. But we can't actually predict what direction that impact will have on virulence. And also for any individual transmission rate improving mutation, we can't actually predict what its side effects on virulence may or may not be. So we might see increases in transmission rate that actually decrease virulence or increase virulence, just depending on this angle of approach and where the starting phenotypes sit relative to the optimal phenotype. And another important point here is that even when pathogen traits are trading off at the Pareto front, the pathogen's optimal virulence strategy can depend on a number of host population and epidemiological characteristics that can change over time. So these can determine which regions of this possible phenotype space are actually selectively advantageous. And so we've discussed how variations in trade-off shape can lead to different optimal phenotypes for different pathogens, but we also think that these optimal intermediate values should change over time and depend on different host and parasite epidemiological characteristics. So I'm just going to get into one of those today to talk about how timescales affect optimal strategies for a pathogen. So an important point about how things evolve in epidemics is that selection can favor high transmission rates when susceptible density is high, even if those high transmission rates come at a cost of higher virulence. And so if we think about kind of how these different strains are moving through a population, we can consider a slower growing, higher R0 strain that produces 3 secondary infections over a 4-day infectious period, and then a faster growing, lower R0 strain. And so when the susceptible density is high, and so kind of every host that these different strains are contacting is an actual susceptible host, these faster growing strains could actually grow faster than within the population than these longer infectious period strains, because they have shorter infection generation times or serial intervals. And so they can produce more secondary infections over a shorter amount of time. And so eventually, as the susceptible supply depletes, we expect that selection should move to favor R0 optimized strains. So this is that slower growing strain that's making a higher number of secondary infections, because these strategies will be more likely to kind of find the susceptible hosts. And so in a public health emergency like a global pandemic, we all understandably want simple answers for how we expect a pathogen will evolve. And unfortunately, the simplest answer is that we cannot definitively predict the evolution of any specific novel zoonotic pathogen. The slightly more complicated answer, though, is that while we can't predict the specifics, we do know how selection is expected to act generally and how emerging zoonotic diseases might differ from these general frameworks. So we know that novel zoonotic pathogens emerge into human populations maladapted to human hosts. And generally, we expect that virulence and transmission rate should trade off, leading to selection for intermediate values of both. We also, though, know that a maladapted zoonotic pathogen's virulence and transmission phenotypes might sit below the Pareto front, and so selection for higher transmission rates might have decoupled effects on virulence. And finally, our theory also says that even with trade-offs, the optimal balance between virulence and transmission changes over time in the epidemic. And so I want to really quickly get at this question of, can we evolutionary manage virulence? Because this is something that often comes up. And so all of these complications mean that public health strategies that are purposely driving virulence to decrease are probably pretty unrealistic, just because we can't predict the evolution, the direction of evolution that well. However, we do know what can limit the evolutionary potential of a virus, and that's simply by decreasing the number of cases, because this is going to decrease the strength of selection relative to stochasticity, and also limit the opportunity for new mutations. And so this means that strong, rapid public health interventions are actually our best evolution management strategy, on top of just being good epidemiological practice. And so with that, I'd like to thank all of my collaborators on this project and open up for any questions.
Great, thank you very much. So Katrina's put her hand right up there. So Katrina, I'll come to you first. Do you have your question?
Yeah, I've got a question. So one thing, it is quite a philosophical question, so
yeah.
I don't necessarily expect an answer. But one thing that you didn't really mention in the talk was, which is obviously really important for SARS-2, is increasing immunity in the population. Once you've got this increasing immunity, which seems to decrease virulence in that individual, it becomes, for me anyway, I get very confused about how we should even define virulence. Do we define it in a completely immune susceptible individual? And should we, I was just wondering how all that kind of fitted into your whole framework, is kind of changing the background.
Yeah, and I think that was one of these things where kind of our broad use of some of these terms meant that scientific communication during the pandemic was really hard, right? Because we can expect to see that virulence, as we define it as just case fatality rates, should decrease over a pandemic, even without any sort of pathogen evolution, just because that age at first infection is decreasing and you have immunity building up in the population. And so most of this theory is really focusing on like specifically on pathogen traits, so that replication rate or site, so kind of the difference between Delta and Omicron and so on. And yeah, I would agree that a lot of this theory doesn't really well consider kind of how host heterogeneity is changing that average selective pressure of virulence. And so is actually kind of
think we may have lost our speaker. Oh, sorry, Elisa, we missed you there for a few minutes.
Oh, sorry.
I think you were, I can't remember where you were at in your discussion, but does that kind of answer it, Katrina? Or?
Yeah, no, it does. I mean, you were talking about the how it is not really well considered in the theories going forward. I think it's great. Thank you. No, that answered my question very well. Thank you.
So there's a couple of questions in the chat. So they ask, does multiplicity of transmission modes and routes enhance pathogen evolution?
So I don't know if they would enhance it necessarily, but they certainly change pathogen evolution. So as part of this paper, we also looked at how traits like that change pathogen evolution optimal strategies, and also how they change over time. And we do expect that certain things like multiplicity of infection should be low at the start of a pandemic when you have fewer cases around, and should increase as the force of infection generally increases, which means it'll be a more important selection pressure kind of at later stages of the pandemic versus early stages. And by routes of pathogen transmission routes, I assume we're talking about kind of respiratory or surface and so on. And that is going to have important implications for kind of which tissues, selection is optimized to try to actually infect. So if we think about pathogen evolution as a trait where where we can't only affect replication rate, we can also affect replication site. Different tissues are going to be more or less important for those different routes. And also things like we have something called the curse of the Pharaoh hypothesis, where certain transmission routes like environmental transmission may allow for higher virulence because transmission is decoupled from the infectious period of the host if it can just sit around in the environment for longer. At the same time, though, we also think that pathogen traits like environmental persistence might actually trade off with other pathogen traits like transmission rate or virulence. And so this theory can get really complicated. And even within the like very simple math, kind of the optimal strategies can move around depending on what assumption you put on it.
Great, thank you. So there's one final question in the chat, but I don't think we've got time to answer it here, but maybe you can try, it's just the last one at 12:02, try and send a message to answer it. But thank you very much, Elisa, and thank you, that was a fantastic talk, and thank you for all the fantastic questions. And with that, our first session comes to a close, and I will hand over to David, who is going to chair our next session on genomic and epidemiological models and techniques. So over to you, David.
Hi there. So